All right, for homework 27, we're starting off with a lot of pre-calc review. Match the function with its graph. Graphs are labeled A through D. So the original natural log of x graph, remember, it has a vertical asymptote at 0, and it has a point at 1, 0, and the graph generally increases kind of slowly like that. So this first, for number 7, I should be looking for a graph that's been shifted up 1 unit, so it should have a point at 1, 1. So that looks to be B. Excuse me. Number 8, negative natural log of x is the y-axis reflection of this. So it should still be going through 1, 0, and it should be a decreasing function, so that's D. This is a shift to the right 1 unit. So if you shift the vertical asymptote from 0 to the right 1 unit, it's now going to be going through 1, so that's A. All that's left is C, but let's take a look at C. So this is both a y-axis and an x-axis reflection. So yes, it should be looking like D, but then reflect D across the y-axis. All right, so sketch the graph of the function and state its domain. So for this graph, the domain you can start with, remember for any log function, the variable or the expression inside of the log for the domain needs to stay greater than 0. So only x values greater than 0 are in the domain here. There's still a point at 1, 0. There's still a vertical asymptote at x equals 0. But the y values are getting multiplied by -2. So the nice points are 1, 0. This graph should be opening down and kind of like stretched vertically a bit. Vertical dilation by a factor of 2. Another nice point that's on there is like at E, instead of being at E1, we should be at like E-2. When you plug in E, natural log of E is 1, multiply that by -2. For the next problem, use the properties of logarithms to expand the log expression. This is important for when we take derivatives. We need to be able to do this. So a root means that this whole expression is to the 1/2 power. And powers, for logarithms, you can take those exponents and multiply them out in front. Then we need to separate this. We have the natural log of x minus 1. It's being divided by x, so it's going to be subtracting the natural log of x. You can't break this down any further. Addition or subtraction inside of a logarithm does not get expanded out. It's only multiplication and division and powers. So that's as far as that goes. For the next one, there's multiplication within the natural log. So I can break this up with addition. This is the natural log of z plus the natural log of z minus 1. Now, it's originally squared, but remember, you can pull this exponent and multiply it out in front. So your final expansion does not have any exponents on the result within the natural log. Okay, let me fix this. It looks like a 7. There we go. So for this next one, now write the expression of the logarithm as a single quantity. It's good to be able to do this, although much more beneficial for our calculus purposes is expanding. But if I needed to, this expression, all of these coefficients out in front can become exponents. So this is the natural log of x to the third times y squared. And then because we're subtracting the natural log of z to the fourth, it would be divided by z to the fourth. Okay, find the limit. Now you can think about this graphically for some of these, like this little graph. It's the natural log x graph, but shifted to the right 3 units. So there's a vertical asymptote at 3, and then the graph is a natural log graph like that. So the limit as x approaches 3 from the right means we're down here getting closer to 3. So that limit is -infinity. The limit does not exist, but we're describing in which direction it's unbounded. And I should also mention this. Remember, with limits, you can just try direct substitution, but the natural log of 3 minus 3 is the natural log of 0. And that's something that we can't do. So that's why we need to investigate the graph. So I mentioned that because of this one. Try direct substitution first, because the limit is not at 4, which is where the issue is. So direct sub, plug 5 in. It doesn't matter if it's left or right. I get natural log of 5 over the square root of 5 minus 4. And that's just a number, right? That's just natural log of 5. So that is the limiting value. You don't need to sketch this graph. I don't know what this graph would look like off the top of my head. But yeah, direct substitution works. For the next one, find an equation of the tangent line to the graph of the log function at the point 1, 0. So remember, for an equation of a tangent line, you need a point, which we were given, 1, 0, and you need a slope. Now the slope is y prime of 1. Okay, so I need a y prime equation. Now, even though this is not that complicated, remember you can expand first when logarithms are involved. So we can say, instead of y equaling natural log of x to the third, we can use our expansion rules. So all I did was expand. The exponent could come out in front. And then this just makes y prime easier to take the derivative of. The derivative of ln x is 1 over x, so this will be 3 over x. So that's our y prime equation. And then evaluate y prime at 1. 3 over 1 is 3. Write my equation. Y minus 0 is equal to the slope, which is 3, times x minus 1. You don't have to have the y minus 0 in there. That's fine. What if you didn't do this? What if you kept it as ln of x cubed? This one's not too bad. But remember, you'd have to do this. The derivative of the natural log is 1 over x cubed. And then this would need a chain rule. The derivative of x cubed is 3x squared. And see how that simplifies to the same thing? You get 3 over x when you reduce this. Okay, so same thing. Same thing for number 44. Let's go ahead and expand this first. 3 halves times ln x. Because then y prime is so easy. It's just 3 over 2 times 1 over x is 3 over 2x. And we're still using the point. We're still using the point 1, 0. And the slope will still be whatever y prime at 1 is. So y prime of 1 is equal to 3 over 2. So y minus 0 is equal to 3 over 2 times x minus 1. If I do it the other way, it's a little trickier. If I keep this, not too tricky, but just I have more to think about here. Easier to make a mistake. If I do this, 1 over x to the 3 halves, you've got to multiply by the derivative of that. So let's think about that. That's 3 halves times x to the, let's see, subtract 2 over 2. So times x to the 1 half. And so you do get 3 over 1 half minus 3 halves is 2 halves, negative in the bottom. So you do get 1 over 2x. But if you subtract wrong or if you make a silly mistake, you might mess this up and then miss an easy problem. It's much better to expand. Now, these problems, you definitely want to expand first because look, if you just start in on the derivative, you would say, okay, f prime is 1 over x squared plus 1. And then what's the derivative of x over x squared plus 1? I'd have to either do quotient rule or rewrite it to be a product rule. And that just is not going to be easy. Here's the other thing. Let's say you do all of that successfully and then you don't see your answer in multiple choice because they would never do it that way. So, okay, so we should expand first for sure. So f of x is equal to ln x minus ln x squared plus 1. Don't overexpand. You can't take that any further. So then f prime of x, the derivative of ln x is 1 over x. The derivative of ln x squared plus 1 is 1 over x squared plus 1. And then we do have to chain rule here, so times 2x. It's the derivative of x squared plus 1. And how much do we have to simplify this? It just depends on what you're doing with it afterwards. So you could leave it here. This is an acceptable answer. If I want to do a common denominator, it would be like over x times x squared plus 1. This fraction gets multiplied by x squared plus 1, top and bottom. This one by x. So you could take it here. 1 minus x squared over x times x squared plus 1. I don't have to do that. But if I needed to do something with the derivative, like set it equal to 0 or whatever, it would be easier to work with this. What about number 70? ln of cosecant x. So You could change this to 1 over sine and then expand it out. I think I'm just going to leave it, see what happens. So this becomes 1 over cosecant x. And then what's the derivative of cosecant? It's negative cosecant x cotangent x. So the cosecants cancel out, and I get negative cotangent x. I would leave it like that. That's also equivalent to negative cosine x over sine x if you did it the other way. For number 77, find an equation of the tangent line to the graph at the given point. Use a graphing utility to graph the function and its tangent line. I didn't do part C, just the direction said A and B only. So, all right, so we need a point and a slope. And we're given the point, 1, 3. The slope will be f prime evaluated at 1. All right, so we need an f prime equation. F prime should just be 6x minus 1 over x. There's no need to do a common denominator here. All you're doing is plugging in 1. So again, you don't want to do more work than you have to and then risk making a mistake. So I'm just going to plug in 1 right here. 6 minus 1 over 1 is 5. So y minus 3 equals 5 times x minus 1. I did graph the original f of x. It looks like this blue curve. And then I graphed this equation, 5 times x minus 1 plus 3 in my calculator. And, excuse me, and this does look tangent, so that's a good sign. Use implicit differentiation to find dy dx. So I would need that for these problems because it's not easy to solve either of these problems just for y. So I'm going to take the derivative with respect to x of both sides of the equation. Remember, that's what implicit is. And I need to remember, anytime I take the derivative of a term with respect to x and the variable is not x, I need a chain rule. So the derivative of x squared is just 2x. The derivative of minus 3 ln y is minus 3 over y. And then the chain rule piece is dy dx. Because you're saying, okay, take the derivative of y. Well, it's with respect to x, so I just write dy dx. Derivative of y squared is 2y, chain rule, dy dx. The derivative of 10 is 0. Factor out a dy dx on this side. That leaves you with negative 3 over y plus 2y. Let's subtract 2x to the other side. And then we can divide. So one possible answer is negative 2x over negative 3 over y plus 2y. It's most likely that they will simplify the compound or the complex fractions. So the only denominator to get rid of is the y. So you can multiply by y over y. That makes this negative 2xy over negative 3 plus 2y squared. Of course, you can rearrange terms and things if you don't like the order that it's in. All right, for number 84, take the derivative with respect to, pause. If I take the derivative right now as it is, I would get 1 over xy, and then I'd have to do product rule. But instead, we can expand. So make this ln x plus ln y plus 5x equals 30. And now take the derivative with respect to x of both sides. Derivative of ln x is 1 over x plus 1 over y times dy dx plus 5 equals 0. Okay, so we can subtract 5 and subtract 1 over x. We can divide by 1 over y, but really that's going to be multiplying by y, right? We could say times y over 1. So that becomes negative 5y minus y over x. You could also say over 1 over y and then simplify the complex fraction as well. All right, for next one, locate any relative extrema and inflection points. So let's start with relative extrema. Those happen when y prime changes signs, so we need y prime. Nothing to expand here. excuse me, y prime is equal to 2x over 2, so x minus 1 over x. Relative extrema can occur where y prime equals 0 or is undefined. So let's get this into a common denominator. X squared minus 1 all over x. Critical numbers are x equals plus or minus 1 from the top or 0. Remember, the domain for this is x greater than 0. Okay, so if we put these on a number line, if I plot all of these, I get 0, -1, 0, and 1. But this domain piece helps us because remember, we can't have any relative extrema where the graph doesn't exist. So I don't care about anything left of -1 or anything negative between 0 and -1. I only care about these two sections. So if I were to plug in 1/2 into y prime, I would get 1/4 minus 1 over 1/2. That's negative. If I were to plug in anything bigger than 1, like 2, I would get 4 minus 1 over 2. That's positive. So y goes from decreasing to increasing. So locate any relative extrema. Let's see what we get when we plug in. There's a relative min at 1. So y of 1 equals 1/2 minus ln of 1. ln of 1 is saying e to what power equals 1. So this is 0. So y of 1 equals 1/2. So there is a relative minimum at 1/2 because, not r, y. Y prime changes from negative to positive. All right, what about points of inflection? For points of inflection, we need y double prime. You don't want to do quotient rule. Just go back here a line and say, all right, what's the second derivative? It's 1 minus, this is x to the negative first, so plus 1 over x squared. And then, of course, you can get that into x squared plus 1 over x squared. What are the possible inflection points? The numerator is never equal to 0, so nothing from the top. X squared equals 0 if x equals 0. Now, again, we don't care about anything negative, so it's really just there's not going to be a point of inflection. If I plug in like 1, I get 2 over 1, so positive. So there are no points of inflection because y double prime is always greater than 0. So y is always concave up. It never changes concavity, so there can't be a point of inflection. Use a graphic utility to confirm your results. So that's here. Yep, this graph looks kind of like a little swoosh, and so that's concave up. Oh, and that was our last problem. All right, come into office hours if you have any questions on this, and I'll see you then.